one of the most interesting and applicable concepts in chemistry is spectroscopy. Spectroscopy literally means measuring light. Measuring light. Why is it so, why is it so practical? Well, maybe it's not extremely practical, but do you ever wonder how we know that the sun is made up of helium and hydrogen? We've never even gotten close to the sun. You can't get close to the sun. You'll burn up. How do we know that the moon, Titan, which is around Saturn, has a methane nitrogen atmosphere? How do we know what kind of elements can be found in Venus's atmosphere? Well, it's simple. Light hits these atmospheres. The molecules in the atmospheres absorbs the light and then emit it in their own sort of way. You see, one of the things you must come to grips with is the fact that every element and every compound has its own particular light fingerprint. Light fingerprint. Just like every fingerprint is a little different, they can identify you by your fingerprint. In the same way, we can identify elements and compounds by the type of light that they emit. Every element and compound will emit its own particular type of light. And over the years, we have learned what kind of light this is. We have measured it, and now it's all in computers. All we need to do is focus our instruments on anything that is emitting light, and we can figure out what kind of chemical it is by its light fingerprint. So you would be able to see the light fingerprint of any compound or element by looking at its spectral lines. Every compound, every element has its own unique way of emitting light. Therefore, it has its own spectral lines. And how do we see the spectral lines? We see it using a spectroscope. So, right here, you would have a slit. That slit would allow light to come in. Over here, you would have an eyepiece that you would look through, and over here, you would have a film that would act kind of like a prism. So, if you had white light, if you were actually taking this spectroscope and viewing the fluorescent lights that are in my classroom, you would get the white light. The light would come through the slit, be reflected off the film, and you would see all the colors of the spectrum. All of it. That's what white is. White is all the colors of the spectrum. Now, if we were to get a particular gas, either an element or a compound, and heat it up, it too would emit light. Its electrons would go into excited state and then come back down into ground state. When it comes back down into ground state, sometimes it emits light that we can see. If it emits light that we can see, then going through the filter, we would see those particular colors as these represented by these lines. And in a spectroscope, you're going to see numbers over here. Those numbers correspond to wavelength in nanometers. So if you were to get some cold light, that white light, this heated gas would emit light as well, but you would only see the parts of the spectrum that is actually being absorbed and not reflected. This is what's reflected. This is what's emitted into your eyes. This is what your eyes do not see. So think of it as the negative of that. All right, this is a much fancier spectroscope. This is the kind of spectroscope that you would find in a college class. So let's heat up some gases and see what kind of light they emit. Now, you're going to look at this and go, oh, this is like neon tubes. Yeah, basically. Okay, so for neon lights, what they're going to use is different gases in order to give you different colors. So we call them all neon lights, just like at one time we call any kind of copies made in a copier a Xerox. Xerox was one of the earliest forms of copiers. So we used to call them a Xerox copy, whether they were made by a Xerox machine or not. Or how about this? Please pass the Kleenex. Okay, actually, it's facial tissue. Kleenex is one of the companies that make facial tissues, but Kleenex was also the first company to make the facial tissue. So when we think of facial tissues, we think of Kleenex. Okay, in the same way, neon was one of the earliest types of gases that we were able to discover would emit these different color lights, and so they all became neon lights, even though really the color is going to depend on the mixture of compounds of gases that are in these tubes. So first up is going to be hydrogen. This is a power supply that's just going to give it electricity. You're going to watch me put the tube. This is a tube of hydrogen. Hard to see the colors, but you can see there is a kind of a purplish hue. If you were to see it in the spectroscope, you would see a red line, a turquoise line, and a darker blue, maybe a violet line there. In a spectroscope, there would be numbers that you could read, and in this case, this is telling us that you have a light emission at 656 nanometers, one at 486, 434, 410. What do those lines represent? Those represent electrons going into excited state, then going back down into ground state. Hydrogen has one electron, not four. What this means is that one electron, you're going to have trillions upon quintillions of hydrogen atoms in that tube. Of all those hydrogen atoms, it's one electron will have a tendency to emit light there, 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 and there. Hydrogen A, its electron could emit there. Hydrogen B, there, there, there. What this is telling us is the most likely scenario for electrons going into excited state and then coming back down to ground state is for it to emit light in these areas. This red represents a little jump down. The green, a medium-sized jump down into ground state. The blue, much bigger, and the violet, much bigger. So, the smaller the wavelength, the closer together the waves are going to be, the higher the frequency. So, red represents low energy, while violet represents high energy. Xenon. If you could see it in your spectroscope, this is what you would see. So xenon has 54 electrons. Most of those don't ever get to excited state. So we're talking about a handful of electrons. This is their spending pattern. I like to think of these lines as representing something that they spend. So they like to spend a lot of cheap items, a little more expensive, and a few very expensive items. So it's like recording their spending patterns They're spending patterns. If we were to give you $100 to spend every Friday and allow you to go to Turkey Creek, after a while we would learn that you have a certain pattern for spending all that money. It wouldn't always be chaotic. After a while you would get into a pattern. Well, what we're seeing is the pattern that the electrons use for releasing energy. Nitrogen. And here are nitrogen spectral lines. Notice heavy in the blues. That makes sense. What's the most common gas in our atmosphere? Nitrogen. What's the color of the sky? Nitrogen. Blue. Helium. Here are the spectral lines that we would be seeing from the sun. That and hydrogen. Helium. Neon. Argon. What you're seeing is what's coming through the slit. You see, that's the light is coming through the slit. That light may appear purplish to us, but purple is a combination of many other different kinds of colors. So this is the tube, and this is the tube, and this is the tube, and this is... So that purple light is all of these colors together. So that when our eyes see all those colors together, we come to the conclusion that that light is purple. So let's go back and to the hydrogen emission spectrum, because it is so easy. And let me prove to you that indeed red represents less energy than purple. In order to do so, we need two equations. E equals, well, that is the Greek symbol that we represent frequency with, and then C is equal to lambda nu. Okay, that's the letter N. The frequency is the letter N in Greek. So here we go. These numbers right here, the 410, that tells us the wavelength. It's in nanometers. The first equation we're going to use is this one. C is equal to lambda nu. All right, I just call it V. It looks like a V to us. We need to solve for frequency. Why? Because frequency is in this equation. This equation has energy in it. See, the big E, that's energy. That's what we're looking for. We need energy. H is Planck's constant, which can be found right there. That's a constant. I'm going to give that to you. You don't have to memorize that number. Nu is frequency. So in order to find energy, we need Planck's constant, this H, and we need frequency. Unfortunately, we don't have frequency. We have wavelength. So that's why we're going to start with this equation. C is equal to wavelength times frequency. We know wavelength is 410. We know C. C is 3.00 times 10 to the 17th nanometers per second. Wavelength is 410 nanometers. let's solve for nu, for frequency. So we're going to have to get 410 to the other side. We do that by dividing. So 3 times 10 to the 17th divided by 410 gives us an answer of 7.32 times 10 to the 14th per seconds. Why per seconds? Because once you divide nanometers by nanometers, the nanometers cross out, leaving you per seconds. That is the number of waves per seconds. That's a lot of waves, but you should expect that because we're talking about light. Light waves are really, really close together. If, when you do this, the answer does not come out to be to the 14th, you've done it wrong. It has to be the 14th. The frequencies that we can see with our eyes are all within the 14th range. So if you're looking at a color, its frequency has to be to the 14th. Now we're going to take this number and multiply it by Planck's constant. Notice you got seconds in the numerator and seconds in the denominator. So seconds cross out, leaving you an answer in joules, which is what we're looking for. Yay! That is a negative 34, by the way. I get 4.85 times 10 to the negative 19th joules. Once again, if this is the 14th, the answer here has to be to the negative 19th. So we're not talking about a lot of energy. But let's erase everything and keep that energy amount the same. And let's solve that energy for the red line. So let's do the same thing, but this time let's use the red line. Okay, so that's 656. 3.00 times 10 to the 17th nanometers per second equals 656 nanometers times V. Okay, so 3 times 10 to the 17th divided by 656. If it's not to the 14th, I've done something wrong. It is to the 14th. So the frequency is 4.57 times 10 to the 14th per seconds. I'm going to put that number right here. I'm going to multiply that number by Planck's constant. Remember, I have to give you these numbers. You don't have to memorize them. 3.03 times 10 to the negative 19th. This is red. This is purple. So, who represents the most energy? Purple. That's why in a dark room, we're going to use red lights. Lights having a gas inside of them that emit only colors in the red zone. Therefore, not energetic enough to develop the film. Do not want purple or blue lights in a dark room.